On 5, looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
Yes, go away.
Ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth. Quite a Christmas present for the world's astronomers as the James Webb Space Telescope begins its life heading towards deep space.
After yesterday's successful completion of Webb Sunshield deployment, mission controllers at the Space Telescope Science Institute in Baltimore, Maryland, are today ready to move on to the next major spacecraft milestone, the deployment of Webb's secondary mirror. In just a few minutes, the team will send a signal to release Webb's secondary mirror support system. Today's activities mark the first in a series of deployments related to Webb's optics. Those beautiful golden mirrors
are fully tensioned.
How exciting.
Significant milestone accomplished. Job well done, Sunshield team. Job well done.
Thank you, Mom.
If you can just tell us what's going on here.
Yep, so you can see the legs come out, and the top leg has a hinge in the middle of it, and it snaps into place, and we're seeing the back of the mirror, so it looks black, but that is one of our colder items. Even when it gets deployed out, yeah, oh, there's a great picture. You can see that the secondary mirror here is at the top of your screen on the dark side, on the cold side, and it does run. It does not have its own radiator, but it runs very cold. It's one of the colder items on that side, and the Sunshield itself is basically what keeps it cold, and the fact that
Carl Starr is you'll hear the acronym, the MOM, the Mission Operations Manager.
دوستان از این لحظه به بعد دقت کنید بازوهای آینه ثانویه داره آهسته آهسته باز میشه. خیلی باید ریز دقت کنید تا متوجه حرکت و باز شدنش بشید.
Ryan, thank you for the update.
There's a nice view on our observatory visualization tool. So you see this giant boom taking the secondary mirror, the focusing mechanism for the James Webb Space Telescope. The primary mirror are those gold segments that you see. There are 18 gold segments. And after we have confirmation that the mirror has been deployed, we'll have some time to look at how those will be focused. That will be another major commissioning activity for the James Webb Space Telescope in the next weeks. This is the largest and most sensitive space observatory ever flown. It had to be actually folded up to fit inside a rocket. This is something that is historic. We have not done this before, where things need to be unfolded to this extent. So this is very dramatic. There are people all over the world so happy that things so far are going well and wishing for a successful deployment. I know that I have friends of mine who've worked on the Webb telescope since about 1995. So this is many, many decades of people's work and life all happening right in front of you live as we watch that secondary mirror deploy.
and some of the things that are unique about this is the operation of these joints in space and at such a cold temperature. We do have a few heaters that we warm up the motors and some of the mechanism components, but for the most part, the joints have to work in the cold environment of space, which takes special design and special coatings. And as you can see, they also are quite close to our mirrors, so we have to be careful about contamination. This is also the first time to do this deployment in zero gravity. Every other time that we've done the deployment in a clean room, we've had to have gravity considerations. So this is the first time doing it in zero gravity.
We were talking about that yesterday with the non-explosive actuators, all of these little pins that need to release to unfold different parts of the telescope. And again, those were all tested on the Earth, where you were not in zero gravity. They needed to work in space. And Julie, I don't know about you, but every time I see that mirror move a little bit farther in our visualization tool, I'm getting more and more excited. My heart is starting to beat faster and faster. For me, there's a tremendous amount of joy. I mean, I have this smile like on my face from ear to ear right now, as I see this absolutely essential component of the James Webb Observatory, the secondary mirror, the focusing mechanism deployed.
Yes, without this mirror in its right position, we do not get light into the telescope.
And all of those actuators, all of those pins that needed to release in order to unfold this. Julie, can you give me an idea?
There's different kinds and different types around, so it's kind of, every time you'll read something, it will tell you a slightly different number, but it all depends on what category they count them in. And for this, what we watched today, there was 3 different ones that we released. So there's so much of that now behind us. There was a lot of work over the years to make sure that these devices worked, and then all the different configurations that we needed them in and the different sizes to make sure that they all worked and they all worked reliably. They're very much like a parachute. They're very sensitive to how they're wrapped and how they're handled. You get one chance to do it right, and if you test it and it works, that doesn't mean that you've done the next one right. So you have to package each one just perfectly. And we're coming very close to being fully deployed. As you can see, the top of the mechanism, the 2 bars there, coming closer and closer to their final position of being in line with each other. And you can, from this orientation, you can now see that the mirror side of the secondary has the gold coating on it too in the visualization tool.
Well, the Webb Observatory is a very large mirror. It's a tiny amount of gold. I believe it's just a couple gold rings worth of gold.
Deployed into the hard stops. So we'll move into capturing the latches and then recentering.
All right, as you heard, that went completely into the hard stop. And they'll take a little bit of time to take a look
at the secondary mirror support structure, and here we have the secondary mirror. Julie, can you tell us what we're looking at in this footage we have?
Sure. So as you can kind of see here, that silver stainless piece is a cover, and then the mirror itself is on a dolly with wheels. And we have engineers and technicians in what we call lovingly as bunny suits in a clean room. And this is, I believe, at Goddard Space Flight Center, doing the initial inspection as they open up the shipping container of the mirror. And now here it looks like we have the mirror up onto the crane and the mechanism to move it up into position where we're going to then do the installation. And here's the people at Goddard watching from the observatory area as the whole assembly takes place. And this is the structure that we were just seeing deployed. You can see it kind of across the middle of your screen, the big booms. And this kind of gives you a perspective of how large in diameter those booms are. You know, they're quite substantial. They look so small in relative to the telescope, But here you can see as we deploy it, here we do it in a horizontal orientation, and they're white there because they have some plastic.
So if there we go. You could maybe talk to this animation.
Sure. So you can see that the bottom two booms are fixed, and the top one has a joint in the center, and that latch is right there at that center joint. And as you come in close, they don't have the details of the latch itself. It's kind of buried in that structure, but right in there, there's a hook latch that comes over to essentially a hard stop, and then it can pull on that hard stop, almost like a tie down type of latch.
To continue
here. So I believe we have some animation. If you could talk to this, Julie.
Yeah, so here you can see like a rather large beam of light coming in from space. It hits the primary mirror, reflects off of that. The primary mirror is concave, and it reflects back. If you run that again, you'll see that the beam is shaped and reflect back to the secondary, which is convex, and then pushes it down through the center of the telescope here. And that is called our aft optics, and it looks like a little nose in the middle of the telescope. And it actually has a couple more optical features in it. It has a mask that you can see that the light crisscrosses right as it goes through that mask, and then it has a mirror and the science data comes down to you. Oh, and here's one of our instruments, and you can kind of see that it's on some spindly legs. The stuff that's putting itself out to the right and the left is the legs, and here's the beam of light that comes in and is folded into the instrument, and then it is folded again, and then once again it's folded. This is our near spec, and then it comes through a wall, and it's into the optics and into the camera into the back. You can see the filter wheel spinning there. Actually, I'm not sure that this is near spec.
These are different instruments that are in the ISIM, the instrument package. Some of the most
I don't actually
sensitive
usually
cameras
see
made.
Yes.
Yes.
This is Muri. Okay. Which is very similar in its four optics there. Apologies, Muri.
We actually have a very good question from Sally Sparks on Twitter, who asks, "How are the steps verified?" We've been listening to the mock today, the Mission Operations Center, and they say, "So this is verified. The engines are on." How are we getting that information?
So we get telemetry. What we have on the telescope is a whole series of sensors of different kinds. We have sensors that are position sensors, we have sensors that are current sensors, we have sensors that are temperature sensors, and all that telemetry gets fed in through the computers and then brought down through the communication system into a ground station, gets sent over to our operations center here in Baltimore, and it comes out on our computer screens. And if
different wavelengths of light require very different observatories. Basically, there's no way to build one telescope that can capture all the wavelengths of light. And you see here that infrared light is the color of light that is a bit redder than our eyes detect. You see that there is an area of this, what we call the electromagnetic spectrum. The electromagnetic spectrum is simply a name for all of the different forms that light takes. And our eyes are only sensitive to a very small range of that, which we call, rather obviously, visible light. There are higher infrared telescopes. The Hubble Space Telescope did see a little bit into the infrared, and we see here an image taken by Hubble in visible light of the famous pillars of creation. These are dust clouds that are many hundreds of billions of miles across, and they are forming new stars and solar systems inside them. And you see here the optical light, but if we switch to infrared light, Hubble had an instrument called NICMOS that saw a little bit into the infrared. These are both actual images, these are both real data, but this infrared image is one their eyes do not see. The information of stars and planets. And this is one of the most active regions of star formation in our part of the galaxy. This is the Orion Nebula. The Orion Nebula is actually visible as a faint smudge below the belt of Orion in what we call the sword of Orion. There are sort of 3 stars that hang down from the belt of Orion. This is the middle, quote-unquote, star. It's not a star, actually. It's a collection of many hundreds of young stars and planetary systems that are forming inside a vast cloud of dust and gas. And while we can see inside the nebula a little bit, where the Orion Nebula is visible to us, it's a much larger complex. And we can see through that dust using infrared. We mentioned the MIRI instrument and also spectroscopes. This is one of the things that's a very powerful way to analyze light. So what a spectroscope does, a spectrograph I should say, is actually pass light through a prism and break it up into the components of the rainbow, all the different of their atmospheres maybe. This is one of the big deals about the Webb Observatory. One of the major goals is to see, do planets around other stars have environments like the Earth, with water vapor, carbon dioxide, oxygen? And the way Webb is going to determine that is by watching that planet move in front of the star, and the star light behind it will pass through the atmosphere of that planet. And as that does, different components will be absorbed, because we know the absorption characteristics of all of these different chemicals, like oxygen, like water vapor. And as that light reaches the James Webb Space Telescope, we'll be able to say, all right, there's a planet going around that star in the sky that has an atmosphere very much like the Earth. And these are some of the signals that we're looking for. Another reason infrared is so important is that some of the most important signals of this absorption take place in the infrared. And perhaps might even have biomarkers, the signals of vegetation. That's less likely. The first thing we'll be looking for is just to find atmospheres that are like the Earth. These are animations, scientific visualizations made of exoplanets. Of course, exoplanets are so far away, we can't yet see whether they have oceans or atmospheres. But these are based on scientific data around a star called TRAPPIST-1. TRAPPIST-1 is a star that we're looking at with the James Webb Space Telescope. TRAPPIST-1 we now know has at least 7 planets, and of those 7 Earth-sized planets that were detected, there are several of them that are about the right distance from the star to have temperatures similar to the Earth. And that's all we know right now, is we know the rough size of these planets. We know that they're dense, they are rocky. And as the planets move in front with the James Webb Space Telescope, we should also have the opportunity to watch the background starlight of their parent star shine through their atmospheres. And when that happens during a transit, Webb will have the power to analyze the chemistry, possibly the temperature and the density of these atmospheres, and determine whether any of these planets have atmospheres that are friendly to light. And that's what you see here in this diagram. You see an exoplanet in this animation moving in front of its star according to our field of view. And different layers of the atmosphere will actually absorb different things, different wavelengths of light in the infrared. And so we'll be able to actually explore what the environments of these planets are like, even from this far away. Right, well, let's go back to the Mission Operations Center.
اینجا فرایند باز شدن آینه ثانویه با موفقیت به اتمام رسید.
All right. So that was Bill Oakes, our program manager. Congratulating everyone on the operations loop.
You're seeing some high fives there.
And what they've done while we were off talking about exoplanets is they confirmed that the latch had latched and took off the tension from the deployment motor. They will continue.
Can you tell us a little bit about that?
Sure. I think, here's our animation. So this is on the back side of the telescope, actually behind the instruments. And you can see right there on the one side of the screen was actually the mirrors deploying out of the way. But this is a radiator that takes some heat from the electronics and all the things that still have to operate on the cold side of the telescope, and directs that heat out into deep space to dump that power out, where it doesn't reflect around and get back into the telescope.
These instruments are designed to operate at very cold temperatures. And after that, we actually now have the deployment of the wings of the main mirror. So what will be happening in the next few days, as you see here, is that the 2 sides of the mirror had to be folded up to fit inside the rocket. This is the largest space observatory ever built. It had to be folded up to fit inside a rocket, and they are now deploying it. And I believe we have footage of the test of the mirrors in the clean room where it was assembled. So if we have that footage to run, Julie, you could maybe comment on what's going on here?
Well, this is back to the secondary deployment that we're doing here. Again, the secondary deployment in a different gravity orientation. And then one last time. In different views, you can see the mirror. Here's the wing coming out. And as you see this, you can see that there's like a black, we call it the frill around the outside of the mirrors. It's kind of like an Elizabethan collar. And what that does is it actually prevents starlight from behind the telescope